We all know that gases do not have definite size and shape. Okay, they occupy the volume of the entire volume of the container in which they are filled actually. They are governed by three parameters. They are pressure, volume and temperature. Keeping one of these parameters constant, the relation between the other parameters is obtained. Okay, the relations between these parameters are nothing but called as gas laws. The following are the gas laws which we actually deal now. Boyle's law right now. It states that at constant temperature, the volume of given mass of a gas is inversely proportional to pressure acting on the gas. The above statement can be written as temperature is kept constant, volume of given mass of a gas is inversely proportional to the pressure, V proportional to 1 by P, implies V equals to K by P, which we can obtain it as PV equal to constant, from which what we can get is P1 V1 is equals to P2 V2. A graph is plotted by taking volume on x-axis and pressure on y-axis. The obtained graph is a rectangular hyperbola. It represents that for large pressure the volume is very small, and for small pressure the volume is very large, isn't it? Okay. Now, in the same manner, we can have the above thing in the pictorial form. As you know very well that when pressure keeps on gradually decreasing, the volume of the gas gradually increases. At constant temperature, these things will happen. Now let us try to understand about Charles' law. In this we study about two variety of laws. One is Charles' pressure constant law. And the second one is Charles' volume constant law. At first, let us try to understand about Charles' pressure constant law. At constant pressure, at constant pressure, the volume of given mass of a gas is directly proportional to absolute temperature. At constant pressure, the volume of given mass of a gas is directly proportional to absolute temperature. From above statement, we have V is directly proportional to capital T, from which we can have V is equals to KT, and we can have V by T is equals to constant, which implies V1 by T1 is equals to V2 by T2. A graph is plotted by taking temperature on x-axis in Celsius and volume on y-axis. The obtained graph is as follows. X dash is the axis and y-axis here. We take temperature on x-axis and volume on y-axis. The obtained graph is as follows. The graph is a straight line having y-intercept. The graph is a straight line having y-intercept. When the graph is extended back, it will touch a temperature called minus 273.15 degrees Celsius, which is taken as absolute 0, and it is noted as 0 Kelvin. The y-intercept of the graph is the volume of the gas at 0 degrees Celsius, which is represented as V0. In pictorial representation, the same Charles law can be given as here the temperature keeps on increasing gradually. As temperature keeps on increasing gradually, the volume of the gas increases gradually. Volume of gas is increasing and temperature is also gradually increasing, which shows volume is directly proportional to absolute temperature at constant pressure. Okay, fine. Now, let V0 be the volume at 0 degrees Celsius, which we take it as 273.15 degrees Celsius, 15 degree Kelvin, and Vt is the volume at T degrees Celsius. Let V0 be the volume at 0 degrees Celsius and Vt be the volume at T degrees Celsius. In terms of Kelvin, we write this as 273 plus T. Okay, fine. Now, according to the law, what we have got is V0 by 273 is equals to Vt by 273 plus t. This I can write as Vt is equals to V0 into 273 plus t by 273. This can also be written as Vt is equals to V0 into 1 plus t by 273, from which what I can obtain this as Vt is equal to V0 into 1 plus alpha into t, where alpha is given as 1 by 273, which is equal to 0.00366 per degree Celsius. Now, the same equation can be written as V1 equal to V0 into 1 plus alpha T1 and V2 is equals to V0 into 1 plus alpha T2. On dividing both of them, we can get it as V1 by V2 is equals to 1 plus alpha T1 by 1 plus alpha T2, from which we can get alpha is equals to V2 minus V1 by V1 T2 minus V2 T1 per degree Celsius it is. Now, let us try to understand regarding Charles volume constant law. Which states that at constant volume, the pressure of given mass of a gas is directly proportional to absolute temperature. At constant volume, it can be stated as at constant volume V equals to K, and pressure is directly proportional to absolute temperature, implies V equals to Kt, P by T equals to constant, P1 by T1 is equals to P2 by T2. A graph is plotted by taking temperature on x-axis and pressure on y-axis. The obtained graph is as follows. Graph is a straight line having a y-intercept. When the graph is extended backwards, it will touch the temperature axis at minus 273.15 degrees Celsius, which is taken as 0 Kelvin, and P0 is the pressure at 0 degrees Celsius. pictorial representation is similar to the volume pictorial representation. Here, as temperature keeps on increasing, the pressure of the gas also keeps on increasing. P0 be the pressure of the gas at 0 degrees Celsius, which is at 273 Kelvin, and Pt is the pressure of the gas at T degrees Celsius, which is given as 273 plus T degree Kelvin. From the law, what we have got is P0 by 273 is equals to Pt by 273 plus T. This I can write it as Pt is equals to P0 into 273 plus T by 273, and Pt is given as P0 into 1 plus T by 273. Here 1 by 273 is taken as beta, 1 plus beta T it is, and beta equals to 1 by 273 is equal to 0.00366 per degree Celsius. From the given equation, what we have got is P1 equals to P0 into 1 plus beta T, and P2 is equals to P0 into 1 plus beta T2. Once more please. P1 equals to P0 into 1 plus beta T1, and P2 equals to P0 into 1 plus beta T2. Dividing one by the other, we have got P1 by P2 is equals to 1 plus beta T1 by 1 plus beta T2, from which beta is equals to P2 minus P1 by P1 T2 minus P2 T1 per degree Celsius. Now let us try to understand the Boyle's law with an application. The application is as follows. An air bubble rises from the bottom of a lake, and its radius is doubled on reaching the surface. If the temperature is constant, the depth of the lake is we have the options as 7 meters, second option as 70 meters, third option as 10 meters, and fourth option as 0.7 meters. An air bubble rises from the bottom of a lake and its radius is doubled on reaching the surface. If the temperature is constant, the depth of the lake is, the options given are, First one 7 meters, second one 70 meters, third one 10 meters, and fourth one is 0.7 meters. And we are given that 1 atmosphere is equal to 10 centimeters, 10 meters height of water column. Now, according to the problem, when air bubble is at the bottom, its radius is r. As the air bubble moves onto the surface of water, its radius has become 2r. On the surface of water, the pressure acting is P0, and at the depth, at the bottom of the lake, the pressure acting is P0 plus h_dg. According to Boyle's law, we have got P1 V1 is equals to P2 V2. P1 is taken as P0 and V1 is taken as 4 by 3 pi into 2r whole cube, whereas P2 is taken as P0 plus h_dg and V2 is taken as 4 by 3 pi into r cube. Substituting the values, we have got P0 into 4 by 3 pi into 2r whole cube is equals to P0 plus h_dg into 4 by 3 pi into r cube. On removing 4 by 3 pi and 4 by 3 pi on both sides and even r cube, we are going to get P0 equals to P0 into 8 equals to P0 plus h_dg. This can be given as 8 P0 minus P0 is equal to h_dg. 8 P0 minus P0 is equals to h_dg. We get it as 7 P0 equal to h_dg. So, according to this, h is given as 70 meters as per the given condition, 1 atmosphere equal to 10 meters. In the previous model, if one of the container is evacuated, in that case, the pressure becomes 0. Let us say second container is evacuated, so that P2 becomes 0. And from the equation, what we have got is P equals to P1 V1 plus 0 into V2 by V1 plus V2, so that P equals to P1 V1 by V1 plus V2. Boyle's law verified. Once more, please. Boyle's law is verified by using quill tube method. By using quill tube. A quill tube consists of narrow capillary tube with uniform bore closed at one end. As shown in the figure. So that a mercury pellet is introduced into the tube and air is trapped near the closed end. When the quill tube is Once more, sir. When quill tube is in vertical position, the atmospheric pressure P0 is acting on the mercury, and the air that is trapped between the mercury pellet and the closed end P1 is also applying a pressure P1. Let length of the air column here in this case is taken as L1. In equilibrium state, the upper pressure and the lower pressure once more please. In equilibrium state, the forces acting on the upper layer is equal to the forces acting at the lower layer, so that P0 into A is the pressure acting on the upper surface plus the weight of mercury mg is also acting on the bottom air column, which is equals to the pressure P1 into area of cross section. Now P0 into A plus m is given as volume into density, and volume can be written as length into area of cross section. So P0 into A plus h into area of cross section into density into G is equals to P1A. When area of cross section is cancelled throughout, then we are getting P1 equals to P0 into P0, P1 equals to P0 plus h dg we are going to get. A quill tube consists of a narrow capillary tube with uniform bore closed at one end as shown in the figure. Atmospheric pressure P0 acts on the top surface, and the weight of the mercury pellet acts on the bottom air that is trapped, and bottom air is also exerting a pressure P1 upward direction. So total upward forces is equal to total downward forces. According to that, we have got P0A plus mg is equals to P1A, okay, and mass is written as volume into density. Volume is given as height into area of cross section. So we get P0A plus HA into dg is equals to P1A, from which we can get P1 as P0 plus h dg. Volume of air trapped is V1 is equals to L1 into area of cross section. From Boyle's law, we have got P0 plus h dg into L1A is equals to constant. The last equation can also be given as h dg plus h dg L1A is equals to constant. From this I can write it as h plus h into L1 is equals to constant. Now let us say the pressure is P2 is acting in that area, so that P2 plus mg, P2 into area plus mg is equals to P0 into area, implies P2A equals to P2A, once more please, P2A plus mg is equal to P0A, P2A plus mass can be written as volume into density. Volume is given as height into area of cross section, so that HA into dg is equals to P0A. Cancelling throughout the area of cross section, what we get is P2 equals to P0 minus h dg. Now P2 is given as h minus h into dg. Let length of the air trapped is L2. Then volume of air is V2 is equals to length L2 into area of cross section. So that P2 into V2 is a constant, implies h minus h into dg into L2A is equals to constant, implies h minus h into L2 is equals to constant. Now let us say that the tube is made horizontal. At this situation, the pressure acting is P0 from the atmosphere and pressure acting from the air trapped is P3. These two pressures are equal right now. P3 equals to P0 implies P3 equals to h dg. Let volume of air trapped is L3. Let once again, let volume of air trapped is V3, which is given as length of the air column into area of cross section. From Boyle's law, P3 into V3 equal to constant implies h dg into L3A is equal to constant, implies h into L3 is constant. Now let the capillary tube with open end upwards making an angle theta with the vertical. Atmospheric pressure acting is P0. Weight of the mercury is acting vertically downwards. Resolving into components, we get mg sin theta perpendicular to the tube and mg cos theta along the tube. Normal reaction is n equal to normal reaction n equal to mg sin theta and P0 plus mg cos theta equals to the pressure P4. Let the capillary tube is arranged at an angle theta with the vertical. The weight of mercury is acting vertically downwards, which is mg acting vertically downwards. Resolving into components, we get mg sin theta and mg cos theta. Mg sin theta is perpendicular to the tube and mg cos theta is along the tube. Atmospheric pressure P0 is acting on the mercury pellet, and here normal reaction n is also perpendicular in upward direction, so that n equal to mg sin theta, P0A plus mg cos theta equals to P4A, P0A plus HA dg cos theta is equals to P4A. Cancelling A throughout, we have got P0 plus h dg cos theta equals to P4. Volume of the air trapped is V4 equals to area of cross section into L4. From Boyle's law, P4 V4 equal to constant, implies P naught plus HdG cos theta is equal into AL4 equals to constant, implies P naught plus HdG cos theta into L4 is equal to constant. The same thing happens when the capillary tube is reversed. Making an angle with the vertical. In that case, what we get is P naught minus HdG cos theta into L4 equal to constant. A quill tube contains a mercury column of length 19 centimeters. The length of air column is 24 centimeters. When it held vertically, on inverting it with its open end downwards, the length of air column will be, the options given are 20 centimeters, 30 centimeters, 40 centimeters and 35 centimeters. Now let us see what happens. When quill tube's open end is upwards, we have H plus H into L1 equal to constant. When quill tube's open end is downwards, we have H minus H L2 is equal to constant. From Boyle's law, H plus H into L1 is equal to H minus H into L2. Here H is equal to 19 centimeters, capital H is equal to 76 centimeters, L1 equal to 24 centimeters, L2 is equals to, we have to find. So L2 is given as H plus H into L1 by H minus H. So that L2 is equals to 76 plus 19 by 76 minus 19 into 24. Okay. On simplifying, we get L2 is equals to 40 centimeters. Now let us consider about ideal gas. A gas that obeys Boyle's law and Charles' law at all pressures and temperature is called ideal gas. The molecules of ideal gas are point sized. Intermolecular forces are absent. అనగా అణువుల మధ్య అంతర్బలాలు ఉండవు. కావున స్థితిజ శక్తి ఏదైతే ఉంటుందో అది శూన్యం అవుతుంది. ద పొటెన్షియల్ ఎనర్జీ ఆఫ్ ద గ్యాస్ ఈజ్ జీరో. వాయువుకు కేవలము గతి శక్తి మాత్రమే ఉంటుంది. ద గ్యాస్ హ్యాస్ కైనెటిక్ ఎనర్జీ. The internal energy of the gas is sum of kinetic energy of all the molecules. అనగా వాయువు యొక్క అంతర్గత శక్తి ఏదైతే ఉంటుందో అది అన్ని అణువుల యొక్క గతి శక్తికి సమానమవుతుంది. వాయువు యొక్క అన్ని అణువుల గతి శక్తి మొత్తానికి సమానమవుతుంది. Now let us try to learn about real gases. A gas that obeys Boyle's law at low pressure and high temperature is called a real gas. The molecules of real gas are finite sized, intermolecular forces exist, అనగా అణు అంతర్బలాలు ఈ వాయువులో ఉంటాయి. The potential energy of the gas is not zero. The internal energy of the gas is sum of potential energy and kinetic energy of the gas. వాయువు యొక్క అంతర్గత శక్తి ఏదైతే ఉంటుందో అది స్థితిజ మరియు గతిజ శక్తి మొత్తాలకు సమానమవుతుంది. An ideal gas of mass m has pressure P, volume V and temperature T. The relation between them is PV by T is equal to constant. Here K is taken as specific gas constant R for unit mass of gas. So it is given as PV by T is equals to R implies PV equals to RT. For m grams of a gas, PV equals to mRT. for n moles of a gas, the gas constant is taken as capital R, which is called universal gas constant, and is given as PV equals to nRT. Put n is equals to small m by capital M, where small m is mass of the gas and capital M is molecular weight of the gas, implies PV equals to m by m into RT. On comparing the equations 1 and 2, we have small r equal to capital R by capital M. Now, ideal gas equation in terms of Boltzmann constant. Constant K. Boltzmann constant is universal gas constant per molecule. It is given as K is equals to R by Na. The gas equation is PV is equals to nRT. Put n is equals to capital N by Na. Then we have PV is equals to n into R by Na into T, implies PV is equals to nKT. Two vessels of volumes V1 and V2 containing a gas under pressures P1 and P2 respectively are joined at same temperatures. Then the common pressure is okay, fine. Let us imagine there are two containers like this. The volumes of the containers are V1 and V2. The pressures of the containers are P1 and P2. The two containers are connected by a valve. When the valve is opened, the gases start flowing from one to another. Let number of moles in cylinder 1 be N1 and cylinder 2 be N2. The total number of moles are N equals to N1 plus N2. From ideal gas equation we have N equals to PV by RT. On substituting we have PV by RT is equals to P1 V1 by RT plus P2 V2 by RT. Here we are given at same temperature, that's why I have considered same temperature for both the cylinders. On removing the RT part, we will be getting PV is equals to P1 V1 plus P2 V2, and common pressure P is given as P1 V1 plus P2 V2 by V1 plus V2, which is actually total volume of the gas. Imagine, let one of the cylinder is totally evacuated. Let cylinder 2 is totally evacuated such that P2 becomes 0. In such case, P is given as P1 V1 by V1 plus V2. In the given graph, the relation between the temperatures is first option T1 less than T2, second option T1 equal to T2, third option T1 greater than T2, fourth option T1 less than or equal to T2. Okay, fine. In the given graph, volume is taken on x-axis and pressure is taken on y-axis. C1 and C2 are the constants. C1 is close to the origin and C2 is away from the origin. The value which is away from the origin is greater than the value which is near to the origin. So, C2 is greater than C1. We know that PV equal to constant, but PV equals to nRT implies T equals to PV by nR, implies T equals to C1, T1 equals to C1 by nR and T2 equals to C2 by nR. As nR is constant, T proportional to C implies more is C, more is T1. As C2 is greater than C1, T2 is greater than T1. Therefore, the option 3 is correct.